Welcome to the Research Highlights video series. These videos are intended to provide a summary of some of the research being conducted by members of the Hopkins Group at the University of Waterloo. This video will discuss our research on Meldrum's acid derivatives. For a more detailed discussion about the properties of Meldrum's acid derivatives, please read our recent article which appeared in the April 2014 issue of the Journal of Physical Chemistry A. Meldrum's acids have garnered a great deal of interest owing to the unusually high acidity of the hydrogen atom that is located alpha to the two carbonyl groups. Owing to the acidity of this hydrogen, it might be able to participate in non-classical CHX hydrogen bonding. Since CHX hydrogen bonds are thought to be important in supramolecular chemistry and in some biological systems, Meldrum's acid derivatives may be good test cases for studying this phenomenon. The mission of this study was to investigate hydrogen bonding in these species, to determine the pathway by which they react, and to see how protonation and deprotonation affect structure. For this study, 3 benzyl Meldrum's acid derivatives were prepared to have substituents which could participate in intramolecular CHO or CHS hydrogen bonding. To determine the structures of the neutral species, NMR spectroscopy was used in combination with detailed quantum chemical calculations. The structures of all 3 Meldrum's acids were unambiguously assigned, and all 3 exhibited geometries suggesting CHX interaction. To quantify the hydrogen bond strength, second-order perturbation theory was used to calculate the interaction energy between the electron density donor lone pair orbital and the accepting CH antibonding molecular orbital. This treatment showed an especially large CHS interaction, which is 3 times larger than the HF-HCl interaction and 50% stronger than hydrogen bonding in the water dimer. The effect of deprotonation was studied using infrared multiple photon dissociation of the isolated anions. Vibrational spectra show that the deprotonated Meldrum's acids reorient such that the proton-accepting substituents move away from the Meldrum's acid moiety. This shows that the acidic hydrogen helps stabilize the compact structures of the neutral species. Of the 3 Meldrum's acids chosen for study, only one could be protonated and isolated in the gas phase. Infrared spectroscopy showed that the H bonding persisted in the gas phase, and that, interestingly, protonation occurs on the phenyl ring. To understand why the other 2 Meldrum's acid derivatives decomposed upon protonation, we must examine the Gibbs energy landscape. First, it is important to note that thermal decomposition of Meldrum's acid derivatives yields carbon dioxide, acetone, and a reactive ketene. Indeed, irreversibly generating this reactive ketene is a desirable feature of Meldrum's acid chemistry. These same products were observed in the infrared multiple photon dissociation process for the protonated and deprotonated species studied here. Our search of the potential energy landscape identified a concerted transition state for the production of CO2, acetone, and ketene products. Interestingly, our calculations also showed that decomposition is a spontaneous process for the neutral and protonated species. Meldrum's acids are actually kinetically trapped behind a large barrier to decomposition. Protonation of the Meldrum's acid significantly lowers this barrier and increases the rate of reaction. For more information about the Hopkins Group members and the research that we conduct, please visit the group website, which is hosted by the University of Waterloo Department of Chemistry. Thank you for your time and your interest in our work. See you next time.